Okay, let me give me a second to get the screen pulled up. There we go. Okay. How did the last homework go? Was that good? Okay, because I'll say that I think that this homework assignment and what we talk about today really does hinge, no pun intended, on your understanding of the last homework. Okay, because what we're going to be doing today, you really do kind of need to understand what we talked about on Wednesday. Okay. And what we're going to do today is about as real world as it gets, okay? And so what I want to talk about today is my singular passion in the field of civil engineering. I want to talk about bridges, okay? And I want to talk about how we use influence lines to perform the analysis associated with bridge design. And then, if you take a course in steel design or concrete design, then you can sort of get a picture of, well, how would we design the bridge? Because I think bridges are, I'm partial to them, but they are sort of I would say a focal point of the focus of civil engineering. There's a lot of different aspects of civil engineering in the prospect of a bridge, not just the structural part. There's hydraulic issues, transportation issues, all that jazz. Okay, everybody get the code? You did not get the code. You did not get the code.
I do my best, Dr.
You do your best?
I do.
Okay. Did you get the code?
No.
Well, we're waiting.
I'm trying really hard. Okay, I got it.
Okay, all right. Okay, so let's talk about our final lecture of influence lines, and what we're going to be talking about is AASHTO. Okay, how many of you have heard of that? I would imagine those of you in transportation, if you've had a transportation class, have heard of AASHTO, the American Association of State Highway and Transportation Officials. I know I've got a couple mechanical engineers who probably like. Am I too mechanical to get that joke, or get that reference or whatnot? So I'll explain. But let's just sort of recap. So we are still using the Mueller-Breslau principle to construct influence lines. And today, like last time, I am going to sort of just give you the influence line. So we are going to be doing a simply supported structure today. And so this is going to be our influence line. I haven't put any numbers on this because, and I did that for a reason. They give me so many of these rolling chairs. Get that out of the way. Okay. So I didn't put any values on this influence line for a very specific reason, and you're going to see why here in a bit. I do want to make sure that we're clear about the rules regarding influence lines. So influence lines are going to equal 1 at the support of interest. They're going to equal 0 at all other reactions. They're going to be linear for statically determinate structures and what have you. And then for internal shears and moments, I think the big thing I want to get across is that influence lines are going to be 0 at the supports. Okay? So the problem that we're going to do today, we're going to be doing an influence line for a bridge, and we're going to say it's a simply supported bridge, and we're going to say it's 80 foot long. Okay? And ultimately what we're going to try and do is we're going to try and record a series of responses at points of interest, and we're going to, the ultimate goal is to develop a big old table of these responses. So I have here on the board a table that we're going to generate for the shears, and then we could generate a similar one for the moments. So what we would do, if you remember how I said we would do this at every 10th point, right? So if we had a bridge that was 8 foot long, we would generate a series of responses at x equals 0, and then x equals, I don't know, there it is. We would generate a series of responses at, x equals 0, and then we would do x equals 8. x equals 16, all the way to 80. Now, if we're talking about internal moment, we're going to have essentially zeros right here and zeros right here. For shears, what we would have are the reactions. What we're going to do today is we're going to pick a particular point on this table. So we're going to pick 37.5. And so we're going to sort of generate sort of a value here, a value here, a value here, etc. across the table. And we're only going to do it at one point, and then you're going to see like what the answer would look like if you did it at every point. And that's where software and whatnot comes into play. But we'll get to that here in a bit. Okay, let's talk about bridges. All right. It is obvious that we need to design bridges for vehicular loads. They have to be strong enough to support the loads that they're going to be subjected to. But we don't design bridges for Honda Civics, okay? I'm being facetious when I say this, you know, but really if you're a bridge engineer or if you're designing a bridge, bridges, the phrase I like to use is the cars are free, okay? In other words, the cars do not produce appreciable load response on a highway bridge. It's the trucks that we need to worry about. And really the term that I want to use is what are called exclusion vehicles, okay? Exclusion vehicles are your sort of statistically upper bound loadings that you would need to consider. So things like concrete mixers, short haul vehicles, things like that, okay? Now, we as engineers could not by any means design a bridge for every single truck that ever would cross a highway bridge in the United States. We can't do that, okay? So what do? Okay? Well, what we do is and not we, I would say, by we I mean the engineering community. What we in the engineering community do is we collect data, you know, across highway bridges in the United States. If you ever hear the term weigh-in motion study, this is sort of what I'm talking about, where what we would do is collect the weights that bridges are experiencing. And what we do is we develop a load model. And that load model represents, as best as we can, you know, there's always a little, you know, whenever you make the model simple, you sacrifice some accuracy, so there's a trade-off. But this load model that I'm going to show you here in a little bit represents as simply as possible and as best as possible the worst case upper bound loading that you need to design highway bridges for in the United States. So the truck that I'm about to show you does not exist in the real world. It is a load model that is intended to simulate worst case scenario truck traffic. Does that make sense? Okay. And that load model has a name. The load model is called the HL93 vehicular live load. It's called the HL93 because the model was developed in 1993. Okay? So the load model that we use consists of three components. Okay? It consists of a design truck, it consists of a design tandem, and it consists of a design lane load. So let me take each of these one at a time. Okay? So the design truck is what we see here. It consists of three axles. Okay? The front axle weighs 8 kips. Okay? So if I were to draw this as like point loads, I would have an 8 kip load, a 32 kip load, and then a 32 kip load right here. Okay, so this axle weighs 8 kips. These two axles weigh 32 kips. Okay, so let's just sort of make sure we're paying attention. So let's take the front axle. If the front axle weighs 8 kips, how much force is each wheel putting down on the front axle? 4 kips, right? 4 kips here, 4 kips here, right? And the axles are spaced 6 feet, or the wheels are spaced 6 feet apart. Okay. So if you wanted a 3D view of the truck, it would be like 4, 4, and then, you know, 16, 16, and then 16, 16. And so the truck would sort of, you know, look like that, if that makes any sense. This dimension here would be 6 feet, which you can't see that on the screen because we're looking at it this way, okay? This dimension here is a constant 14 feet. This dimension here varies anywhere from 14 feet to 30 feet, okay? It is your job as the engineer to vary that spacing as much as needed to generate the worst case response. So just to make sure we're clear, this is 14 feet, this is 14 feet to 30 feet, okay? Let's just sort of like use some common sense. If I have a bridge that's 80 foot long and I want to generate the worst case bending, should I make that value 14 feet or should I make it 30 feet? 14, because what I would want to do is lump the loads as close to the middle as possible, right? So some of you might be wondering, like, well, why is it variable? There are two reasons why it's variable. One, if you have a really odd span arrangement, there might be a scenario where 30 feet generates the worst case response. That's probably not that likely in most practical settings. But the second reason is that whenever you're assessing the limit state of fatigue in bridge engineering, you keep it at 30 feet. So, but we're getting way into the weeds on bridge engineering land there, so we'll just sort of move past that. Okay, now that's the truck component, okay? The tandem component is intended to simulate like really heavy concentrated loads. It's like, imagine you're driving down 64 and you see a truck hauling like a really heavy load. That's sort of like what the tandem is, okay? And the tandem, let me break out my eraser. Are y'all okay if I erase my pretty little picture here? You okay with that? Okay. So the tandem is just two 25 kip axles that are spaced 4 feet apart. Okay? So that's basically it. Okay? And again, it's intended to simulate really heavy concentrated loads. The design lane, remember how on Wednesday we were saying there's a live load of like 1.6 kips per foot? Where do we place the load to generate the worst case response? For AASHTO lane loads, instead of 1.6 kips per foot, it's 640 pounds per foot. So 640 pounds per foot is sort of intended to simulate the vehicular lane of traffic on the bridge. Okay, does that make sense? So what you would need to do as an engineer is you would need to deal with all three of them. You would need to get a series of responses for the lane, a series of responses for the tandem, and then a series of responses for the truck. What you would then do as an engineer is you would combine them with these statistically calibrated load combinations and then use that combined load, and that's what you would design with. That part is really easy. Like if you have this data and this data and this data, combining them takes about 5 seconds. The hard part is getting the data, okay? And so that's kind of what I want to go through today, okay? Does that make sense? Okay. Now, what we're going to do is we're going to apply the AASHTO load models to a bridge that's 80 foot long, and I want to get the data. I said 37.5. I know why I said that. I'm sorry. I didn't mean 37.5. I said 30. I meant 30. I know why I said 37.5, and you'll see why. But we're going to do this envelope, and I want to get the data in this row for x equals 30 feet. Okay? I know why I said 37.5 because I was using that number there, so bear with me. Okay. All right, so one of the things that's worth mentioning is I've already given you the influence lines. I think for a problem like this, constructing the influence lines is pretty easy. I hope everybody's okay with that. So I'm giving you the influence lines, and I want to figure out what is the worst case shears and moments due to my three loads. You know, worst case positive and negative shear, positive and negative shear, positive and negative shear, and then we'll do it again. Positive, negative moment, positive, negative moment, positive, negative moment at 30 feet. Okay, and again, that would just be one row in the table, and then we would do this over and over again. Okay. Let's see. Okay, so let's see what we can see. Where did my pen go? Where did my little pen? Oh, there it is. Okay. So I'm actually going to do this sort of in the backwards order that I described it. Like I described the truck, the tandem, and the lane. What I'm going to do is do it in the order of the lane, the tandem, and the truck, because I think it gets harder as you go. Okay? So just bear with me. Let's see what we can figure out. Okay. So let's see. I am going to cheat a little bit here. Bear with me. I'm going to cheat a little bit. Are you kidding me? Why does this always happen? Let's try something here. If this doesn't work, I'm going to get upset. Okay, for some reason, OneNote likes that, but it doesn't like the other one. Okay, so if you notice what I'm doing, I'm kind of being a little lazy here, and I'm pasting these images over and over again, mainly because I don't want to have to scroll up and down again. If you're writing this in your notebook, it shouldn't be that big of a deal. Okay, so what we're going to do is we're going to handle each load one at a time. Let's start off with our lane load. Okay, so the lane load is admittedly the easiest one to deal with. Oh. So our design lane is 640 pounds per foot. Okay? So our design lane is 640 pounds per foot. And so what we're going to do is we're going to place that lane load wherever we need to generate worst case response. So we've done this before. Okay? Where would we place, so if we were looking at shear, where would we place the load to generate worst case positive shear? We'd place it from here to here, right? What about negative shear? Here to here, right? What about worst case positive moment? Everywhere. Okay, how about this? What about worst case negative moment? Nowhere, right? There is nowhere that you can place the lane load to make the beam frown at you, right? Make sense? Okay. I just want you to keep that in the back of your head. Okay. All right. Now, a couple things worth mentioning. I'm going to do some intermediate calculations for you because I don't want this to be an exercise in geometry. Would you believe me if I told you that that area is 15.625? And would you believe me if this area is negative 5.625? Would you believe me there? Would you also believe me if I told you that that area is 750? I mean, what do we have? We have 18.75 times 80 over 2, so 18.75 times 40, right? Does that, everybody believe me there? Okay, so here's what I'm saying. I'm saying that if I have the worst case positive lane load, what I'm going to say is, well, first off, let's do this. Note, let's say that 640 pounds per foot is 0.64 kips per foot. So I'm just going to say 0.64 kips per foot times 15.625 feet. And when you chug that out, you should get, it's actually pretty even. It's 10 kips, and then V lane minus is 0.64 kips per foot times negative 5.625 feet, and that ends up being minus 36 kips. So what I'm saying is, under the lane load, this point on the beam would see a range of shear anywhere between 10 kips and negative 36 kips. Does that make sense? Wait, did I get that backwards? 3.6. 3.6. Sorry. 3.6. Here, that was a very understandable questioning look from the class. Hold on, Dr. Mike. There's this thing called arithmetic. What's going on here? That's a fair point. Okay. All right. So similarly for the lane load, for the moment, we're going to have a positive times 750. And again, for you units, folks, that's 750 square feet. That's 480. And then what did we say this is going to be? 0. In fact, let me just ask a general question. Are we going to have any negative live load moments on this bridge at all? No. Could we ever? I mean, not on this bridge, but could we ever have yeah, of course we could. But not on this one. And the reason why we could is if we ever had a moment influence line that had negative area or negative values, well then of course we could, right? We don't have it on this problem, right? So we don't have to worry about it. Okay, so what was I getting at here? So here's what I'm saying. Like this, what I have here on the board is just for shears. So I would say that this value here, we'll say that this is positive 10, this is negative 3.6. Everybody okay with that? You're probably like not seeing where this is gonna go, but just give me a little bit of rope on this one. You'll see where this is going here in a bit. Sound good? Okay. Okay. Now, before we move on, I want to see if this makes sense. Is everybody okay with this? No questions. Okay. Then I'm going to start ratcheting it up a little bit with the design tandem. So let me bring this up here. Okay. Now, remember, what does the design tandem look like? Here's the ground. That's what the design tandem looks like, right? Okay. So let me see if I can like paint the picture, okay? I have a design tandem, okay? So I want you to imagine that I have two loads that are 25 kips each, right? The distance between them is fixed at 4 feet apart, okay? So let's look at my little diagram here on the board, okay? I need to figure out where to put these loads on the bridge in order to generate the worst case response, okay? So let's start with positive shear, okay? Let's start with positive shear. So we agree that this is going to be my positive area. This is going to be my negative area, right? So is everybody in agreement that if I want to generate worst case positive shear, I don't take those loads, stick them here, right? Everybody okay with that? I need to take those loads and I need to stick them somewhere over here, right? Where over here? Do I stick them here? Do I stick them here? How about as close to this? So maybe what you're saying is I need to have a load like right here and then a load like right there. That is the worst case positive shear that I can generate right there. Is that okay? Okay. So what that's going to require is a little bit of linear interpolation. Okay? So I know that I know this value here is 0.625. I need to figure out this value right here, right? So we'll call this, I don't know, we'll call it H1, right? So how do we do that? 0.625 is to 50 as H1 is to what? 46. Right? Because if that is 4 feet, right? That is the tiniest number I think I've drawn this entire semester. But if that's 4 feet, that makes this 46, right? Does that make sense? Okay? So, therefore, this implies that here, I'll lower this down just a bit. And what is that? 0.575. Is that okay? So, all right. Okay. Now we're not talking about negative shear right now, but can anybody? So we did this one. We did this interpolation right here. Now we didn't. We're not talking about negative shear right now, but can anybody peer through the crystal ball and see another interpolation we're going to have to do? We're going to have to do this one, right? Right? And so why don't we do that? Why don't we go ahead and just recognize that we're going to need to do negative 0.375 is to 30 as H2 is to what? If this is H2, 26. Oh. And that's going to be 325. Is that fair? Sound good? Okay. So let's go ahead and do the tandem then. So how am I going to do this? What is the worst case positive tandem? How do I compute that? Like, you tell me what to do. Remember, the tandem is two 25 kip axles spaced 4 feet apart. How do I do it? It's not a distributed load, they're point loads. So with distributed loads, you take the influence or the magnitude of the load times the area under the influence line. How do you deal with point loads?
4 kips times 0.625.
4 kips?
Oh, 25 kips.
All right, so 25 times this plus 25 times that, right? Does that make sense? So this is going to be does that make sense? And what is that going to be? $30. I picked a value, or I picked a space that I thought would have really, like, I wanted the numbers to be kind of easy to deal with. So V tandem negative I'll go ahead and do this one for you. Would you agree with me if I said that? So we'll say that. Sound good? Okay. Now, let's think a little bit about the moment. Okay? Let's think about this. I did my best on the board here. I mean, it's perfect on the screen, but I did my best here on the board to try and draw this to scale. Okay? I have 25 kips. Where is one of those 25 kips going to go? Right here, right? Okay. Where's the other one going to go? And so here's my question. Is it going to go right there? It's going to go right there, left or right? Right. Because this value right here is going to be higher than this one, right? So the worst case placement is going to be over here, not over here. Right? Does that make sense? Okay. All right. So let's work our way through that. And by the way, just to sort of like make the point, I did do the interpolation on both sides. Is it okay if I just give you the values? So I did do the interpolation on both sides. And when you do it, you get 16.25 here. And you get 17.25 here. So therefore, you would say 25 kips times 18.75 feet plus 25 kips. And then you would use the larger of the two right here. And that comes out to be 900. And by the way, again, what is that? Say it again. 0. Okay. Okay. Sound good? Okay. All right, let's talk about the truck now. Okay? Let's talk about the truck. So the truck, see, now you can see why I cheated. Because I didn't want to have to scroll up and down. That would just be a nightmare. Okay. All right. So, again, what did we have? We said that the truck, 8 kips, 32 kips, 32 kips, 14 feet, and then we said 14 feet to 30 feet, right? That's the model. Can I ask you a question about bridge design? Is there anything on that model that says the traffic's going this way? Well, that's how I drew it, but does it have to go that way? Like, what I'm getting at, is there anything that says the truck can't go the other way? Vehicles can drive either way on the road, right? The model doesn't care, okay? So what I'm saying is you can reverse the order. And you might be wondering, what's the point? What are you getting at? Okay. Do we agree 14 feet is the number that makes sense, not 30? Okay. So here's what I'm going to do. On the shear diagram, let's do shear first. On the shear diagram, what I'm going to do is I'm going to interpolate 14 feet out, 14 feet out. And then over here, 14 feet out, 14 feet out. And I just realized I said shear diagram, not shear influence line. Bad. This is the influence line, not the shear diagram. Okay, so let's go 14 feet out either way. Are you all comfortable if I just give you the values? So this is 0.45, 0.275. This over here, 0.2, negative. And this, negative 0.025. And I can see a question coming up, which I'll address here in a bit. Well, I'll do it now. What happens if it goes off the bridge? Just ignore that axle, and you'll see what I mean here in a second. Okay. So, all right, so let's do V truck positive. So we're going to have a load times 0.625 plus a load times 0.45 plus a load times 0.275. Okay. So what do I put here? Do I put 8, 32, and 32?
No.
I put 32, 32, and 8, right? I face the truck, whichever way is going to generate the worst case response. And when you chug this out, you get 36.6 kips. For V truck negative, so let's do the influence line indices first. So the influence line indices, so if I go, let's just say I go from left to right. So bam, bam, bam. So negative 0.025, negative 0.2, negative 0.375. So what order do I place the loads? Is it 8, 32, 32? Yes, right? Because that's the worst case value, right? So 8, 32, 32. And so that is negative 18.6. So what would go in our final columns? It would be plus 36 and then minus 18.6. Okay. Now, okay, for moments, okay, so how do we do the moments? Like, how do we handle this? Okay, here's how I do it, is I don't try and be predictive. What I'm going to do is, we agree 14's the distance, right? So what I'm going to do, let's just interpolate 14 foot on either end twice to see like what values we should use, okay? Like let's just go 14, 14, 14, 14. Is everybody kind of okay with that? So if you all are comfortable with this, this one ends up being 1.25. This is 10. This is 13.25. And this is 8.25. Okay, so let's see if we can reason through our load placement. Which of these is the largest value? Okay, so what axle should I hang right here? Okay, now what's the next highest? Okay, so what axle should go right here? Now what's the next highest? And what should go right here? Does that make sense? So just cycle through it, you know? So okay. When you chug that out, you'll get 1104. And again, that's going to be 0. Does that make sense? So this is the range of moments and the range of shears for which you would design. So if you want to know what the answer is all these values. Okay? Does that make sense? Okay. Does everybody feel comfortable with this analysis? So if you were to ask me like what I call this process, sometimes I call it live load generation. That's kind of what I call it, is to generate the range of live loads for which we need to design. Make sense? All right, any questions? All right, I got a couple things I want to say, and then we'll call it. Okay. All right, so let me say a couple things. So we did this at x equals 30 feet. Okay? Now, I picked an arbitrary point, and some of you are probably thinking, well, wait a minute, Dr. Mike. You said 10th points. 0, 8, 16, 24, 32. 30's not on that list, right? You're right. It's not. Okay? Okay, so let's talk about that. All right? Engineers. So first off, would everybody agree that you're going to have to do this a lot? Like you're going to have to do this a lot. Okay. So the first thing that's worth mentioning is that you'll notice I didn't give you any values here because really I think what might be valuable or a valuable exercise is to figure out how to draw an influence line at some distance x away as opposed to 30 feet away or 40 feet away or 45 feet away. Do it at x away. And you can actually derive pretty simple formulas for this, that this is negative x over L. This is 1 minus x over L. Okay? This point right here is going to be x times 1 minus x over L. And if you don't believe me, take L is 80, x is 30, plug it into the problem we just did, you'll get the same influence lines. Okay? So what I am saying is that bridge engineers will do this at 10th points along the span. So what they will get is this, okay? So this is what you would get if you went and you did this at 10th points, is you would get an envelope like this. So what I have here, this is the envelope of shears. This is the lane, the truck, the tandem. I did it backwards. I did truck and tandem as opposed to tandem and truck. Lane, truck, and tandem. These are the shears. These are the moments. Does anything pop right out right here at the moment table? 0 in the negative columns, right? Because there is no negative moment on a simply supported bridge, okay? We would just do it at every 10th point, okay? Now, some of you might be asking, well, again, Dr. Mike, the 30 feet, that's not in the table. Like, why are you doing this example, okay? Because I want to make a point, okay? In the real world, you could do this one of two ways, okay? The first way is you could do this analysis at 30 feet, or the second is you could take your 10th point responses and just linearly interpolate. So let me give you a motivating example. Let's say that you needed to determine the shears and moments 30 foot away from the support, because right there you have a connection, or you have a splice plate, or you have a cross frame, and you need to know the forces at that point in order to be able to design and detail it, which is a very common thing that you'd have to do in a bridge analysis or a bridge design. So one way of doing that problem is to do this. Okay, now if you do this at, 30 feet, these are the answers. So these are the answers for shear. Okay, but couldn't you get close enough to these answers by just linearly interpolating? Like, let's take a look at the truck envelopes. So this is the worst case positive shears. This is the worst case negative shears. So at 30 feet, what do we get? We get about, this is 20 and this is 40. So what is that, about 35, 36? What do we get right here for the negatives? This is 0, this is 20, a little bit higher, maybe about, I don't know, 18. Is it going to be exactly the same? No. Because you can follow these patterns and see this is nonlinear. This is nonlinear too, right? But what I'm saying is if you do it at 10 points, it's close enough that you can interpolate between them and you don't need to do this analysis at particular points along the span if you have something you want to look at. Does that make sense? That's why bridge engineers will do it at every 10 points, okay? So like if you were to linearly interpolate versus what we do here, the answers are going to be slightly different, but close enough for government work, okay? Make sense? All right. Now I'm going to show you my next slide. I think it's the most dangerous slide I'm going to show you this whole semester, and I want to explain why. Okay. Everything that we have been doing has been influence lines for determinate structures. What if the structure is indeterminate? Okay. If the structure is indeterminate, the influence line can curve. Okay. Because if I take, let's take the best example is the influence line for the reaction at B. So how do I draw the influence line? I take that structure and I kick out the roller support from B, and then I move point B through a unit displacement. But if I remove the support at B, that's a simply supported beam. So in order to pick point B up, I have to deform the structure, right? So it's gonna curve, okay? But the reason why I say this is a really dangerous slide is this is only for structures that are indeterminate, okay? So if I give you an exam problem, for example, and it's a determinate structure, don't do that, you know? Don't do that, okay? Does that make sense? Okay, so and I'm just gonna tell you, I'll just level with you. You know what, I'm just gonna say it right now. I'm not giving you an indeterminate problem where you need to develop quantitative influence lines on the exam. I'm not doing it. So, no. Now, in the real world, if you had a two-span bridge that was a continuous span, yeah, you're going to have some curved influence lines. That's where software comes into play. That's where Masthand would do this or something like that. You would just develop a finite element model and then do it at every 10th point and record your responses. Most bridge engineering software programs will do that for you. So, like, if you look at most modern bridge engineering software packages, what'll happen is you'll have the ability to generate a report at the end, and if you run that report, you'll get data that looks something like this, and I want you to kind of understand what it means, okay? That's kind of the idea. In case you have a bridge engineering project sometime in the future, I don't know. All right. Sound good? I don't know what you're going to do in capstone. I got no idea, so I'm just throwing it out there. All right. Any questions? Okay. All right. This is it for influence lines. I have one homework for you. But what I want to tell you is next week, we begin our last topic in this class. And our last topic in this class is what's called matrix analysis. Okay? So I'll say a couple things about matrix analysis and then I'll let you go. If you open up your textbook has a bunch of different ways to compute deflections. There's geometric methods, there's energy methods, there's conjugate beam, Castellanos method, direct integration, all this stuff. I only showed you one. I showed you virtual work. And the reason I showed you virtual work, it is the one method that will work for any problem. There are some methods that work better, but this is the one method that works for any problem, anytime, okay? That's why I like it. If you open your textbook, there are multiple ways to analyze an indeterminate structure. That's something we haven't actually talked about in here, really, is how to analyze a structure that's indeterminate. We have not done that yet, okay? We have not done any problem like that. There are multiple methods. If I'm going to show you one method, what method am I going to show you? And the answer is, I'm going to show you what Masthand does. Or more specifically, what any structural analysis software program does. I don't care if it's RISA or STAD or SAP or Masthand or even some more advanced stuff like Abacus or COMSOL or ANSYS or NX Nastran. They all operate according to the same philosophy of analyzing a structure through matrices. Okay? Now, I'm going to tell you that we are going to do some matrix math, but we're not going to use MATLAB. We're going to use Excel. Because I have a feeling, like when I bring up MATLAB, it is as if, I should bring, holy water or something, We're not going to do that, okay? But we are going to do matrix math. So we're going to do things like matrix multiplication, inverses, stuff that Excel can do for us, but you're going to see it. So we're going to talk a little bit about that on Monday. But that's all I got, everybody. I will see you all then. Here's the code in case you missed it.